Hello everyone, this is lecture 27, second to last lecture of PTRE 451545. Today we should be finishing module 4 and we will start module 5, which we should finish next week, next lecture. It's fairly quick. The project was due last night, so now you are done completely with the assignments. We have to grade them, and then we just have one thing left, and that is the final. The final is comprehensive. It's gonna be like everything that we covered in the class. There won't be most likely a lot of review, but I can arrange maybe if you want a session, if there is demand, I can have a session. Office hours today, I will move them to 12 to 3. We have a candidate coming up, and then what time is his mock lecture?
I think
He's at, but I have a dinner with him later at 6:30, and then I have a. I will probably join it online.
I think the mock is supposed to be 1:30.
Oh, 1:30? Okay, yeah, I mean, regardless, I will have my office hours at 12 to 3. I don't think anybody would come, to be honest, to the office hours because, yeah, I might have Kalu come over and practice his presentation with me. But anyway, so that would be, today we should be finishing module 4. Now we have done most of the stuff in module 4. We covered them. And we saw the video of how you feel the marine riser, and we talked about it. And we finished somewhere here. When we were talking about the Macondo, back to when it was called Gulf of Mexico, and we talk about the differences between Macondo and the A-21 well in Santa Barbara, 1969. The main difference was that there was a very, very big section underneath the well in Santa Barbara that was left uncased. And when the pressure went up when they shut it in, pressure started, we had a series of underground blowouts, which helped oil to migrate from the reservoir into the seawater. In Macondo, this did not happen. The well was deep enough, it was cased well, and it lasted. But so in Macondo, the only problem was the actual blowout and what happened after. There wasn't any underground blowouts and further leakages after the shut-in. The shut-in was okay. Now, one thing that came out from Macondo, legislation-wise, it's the worst-case discharge estimates, which basically tells you, by law, if you are going to drill a well offshore, you have to estimate, before you start drilling, what we call WCD. That is flow rates and volumes that you expect to face if there is a blowout. So if I'm drilling a well there, and I'm going to have a blowout, I know in 30 days the flow rate will go from this value to that value, and I'm going to have this volume inside the spill, etc., etc. And the reason they make you calculate the worst case discharge is that so that they know what kind of equipment they need to have available to face the oil spill and for contingency purposes, basically. Now, calculating worst case discharge is a complex approach. It can be as complicated as you want to make it. My advisor for PhD used to calculate worst case discharge for Chevron. And I know that Chevron was doing, at least at her time, they were doing it even for onshore wells. They were calculating WCDs for any well that they were drilling, not just offshore well. She had a student who did her master's on worst case discharge estimates using cross flows from different zones. It's a lot of stuff that matters when you calculate this worst case discharge. Because you can be producing from different zones, etc., etc. Now, if you know Hakim, he was TAing for this class last year, and his PhD project is using worst case discharge to predict, to come up with a schedule of how to shut in the well after a blowout. So he goes one step further, saying, if you have a blowout, this is the rates that you're expecting to get, and from those rates, this is the shut-in schedule that you should implement to get a safe shut-in. So we make use of this estimate, which is, we make it useful for another reason. We take it one step further. Now, SPE in 2015, I believe, they published a technical report on how to calculate this. I think it was called worst case discharge calculations, something like that. And like I said, you can get as deep as you want to get onto that topic. You can do it using IPR and VLP curves that we learned in the other class, the well completions class, basically production stuff. And you can add any complexity as you like. You can add like cross flows, etc., etc. Now, and this is mostly a reservoir or production-related problem. Now, key differences between Macondo and Santa Barbara was the main one is the one I already mentioned, that you have casing all the way down in Macondo. You didn't have casing all the way down in Santa Barbara. But in Macondo, you had a weak point at the rupture discs of the 16-inch liner, about 9,000 feet. 9,000 feet from the sea level. There were some rupture discs. What they call rupture disc is basically like an a fuse is to an electric circuit. You put a fuse there to break early before something more valuable in that electric circuit breaks if the current goes too high, right? So you sacrifice the fuse not to break something more fancy and more expensive on your electric circuit. Here you have the rupture discs. So if the pressure inside the liner goes too high, above a certain level, those rupture discs are supposed to break and leak some mud outside so that it relieves the pressure. And once the pressure drops below a certain level, you will be fine. Now, after the blowout, there was 86 days of discharge from over 60,000 barrels a day to something like 53, which is a lot of oil flowing through, very high flow rates, basically primary recovery. But there is a lot of sand coming up with it, with those high flow rates, because when the flow rate is very high, you get fines migration. Imagine what kind of fines migration you are getting in this case. And the sand abrades the inside of the casing, the inside of a liner. The liner is just like casing, but I mean weaker, basically. So the rupture disc is a weak point of the liner. So if something in the liner is going to break, it would be the rupture disc. And there wasn't a question if they were going to break during the discharge, because during discharge, the pressure at the inside the well is small because you are flowing. But when you cap it, the pressure will go up, right? And if the pressure goes up, it's a question whether the well will sustain it. And the vulnerable point was the casing, the rupture disc. Now, the other vulnerable point, I guess, is the casing should depth, but that was too deep to have an issue. And the government put together a team of engineers between the national academies, BP, and several people, even from universities. And they came up with a plan. They said that we are gonna shut in the well and monitor the pressure. If the pressure goes above a certain level, which was like 7,500 psi on the capping stack here at the top of the seabed, it means that the well is safe. It can hold pressure, so we are good. If the pressure plateaus below 6,000, we need to open the well because we definitely have leak somewhere, and we need to see what we are gonna do. It wouldn't be a good outcome, but at least prevent what happened inside the bottom. The truth, what actually happened is that the pressure got just between those 2 points, between 6,000 and 7,500, where they said if it goes in between, we're gonna discuss. And it went in between those values, and they said, okay, let's monitor the well to see if we get any leakages in the surrounding area. And they didn't really get indications of leakage around, so they basically shut in the well. They basically proceeded with permanently capping the well. But you understand that when they said, wait and see how the pressure goes up. If it goes above a certain level, it means that we don't have failure, we are good. If it goes below a certain level, it means that we are losing fluid somewhere. That means we have leakages, which can become something like Sadabarpan. So this is what happened. Now, this is the capping stack that was used. And it was a custom-made capping stack. It goes onto the broken blowout preventer at the seafloor. It's smaller than the blowout preventer. The blowout preventer is yellow on the seafloor. And basically, it works like a blowout preventer. It has rams. It has a lot of chokes, similar stuff that you know how to use in a BOP. But yeah, its job is to get attached onto the broken, damaged BOP, and basically facilitate the shutting of the well. Now, when you are drilling an offshore well, you need to have like 2 capping stacks that can do the job if your well has a blowout within, I don't know how close to your platform or available and ready to go. Something like that. And there is, it is operated with remotely operated vehicles. It's an engineering nightmare to operate. It's bigger than what it looks here, but it's not as big as the blowout preventer. And they call it the big brother of the blowout preventer because it's gonna basically get attached and finish the job that the blowout preventer should have done. Yeah.
So that was the earlier slide before this one where you spoke about how you spoke about the Rapture. Rapture-based lineup, 16 lineup. That's where it works like a stabilizer or a regulator, where the pressure or it goes beyond what it can contain. They said, okay, go off, and then so that you can save other stuff. So I want to know whether after the Macondo or Deep Horizon incident, do they revise any of that so that maybe in case of any other?
Yeah, they revised a lot of stuff in terms of wellbore architecture. From a legislation perspective, I guess what you need to do for designing a well, and you should know that like those wells, offshore wells, they take many years to design them. Like the average time to plan an offshore well, I read one time it was like 7 years to plan an offshore operation. And of course, these are averages. But yeah, I mean, it's a lot of stuff that go on when you're gonna drill offshore. And don't forget that you're gonna be drilling in a very overpressure region. So it's not easy. And this well was the first well in that, look at that name, MC, Mississippi Canyon 252, that's the block, #1. That was the first well.
Well, in that field.
Yeah, it was the first well in that field. It was basically the wildcat. So, okay. So they were, yeah. And if you see the estimations, the calculations they were making to see how the pressure will go up, I talked about them in the other class, they were fairly simplistic. And the simulation model they used is more simple than like class projects that we do. Like it was very, very simple models that they used for that. And they used some well testing equations to predict how the pressure will build up after you shut in the well, because eventually what this becomes is basically a well testing problem. Like pressure build-up testing problem. It's like you are producing the well for 86 days, and then you shut it in, and you want to see how high the pressure will go up. So these are the calculations that they had to make and see like whether you are gonna hold. Now, when the pressure goes up, it won't go up as high as it was before because of mass balance. Of course, it might spike because of dynamic effects like what we call water hammer and some wellbore storage stuff. So it might spike higher than what it was before momentarily. Now the question is, will the rupture disk hold? And the rupture disk would have held well, but because of these 86 days of abrasion with sand, nobody knew in what state the rupture disks were. Now, once they shut it in, and they were convinced there is no leakage around, they shut it in on July 15, and they kept monitoring. The blowout happened in April 20th. And then they drilled a relief well, like, let me show you. Once the well is shut in, you can come here next to it, let's say drill a relief well, intersect it, and then pump cement. Fill it up with cement.
Okay.
And then basically it's safe.
Oh.
Permanently killed.
So that was what they did.
It was September 30th when Obama declared, or September 3 or September 30th, that Obama said that it's safe. It has been flagged completely. Yeah.
For me, I'm just curious about the Macondo well. The time lag it took them to be able to contain the well. For me, it's a very long time.
Yeah, it was 86 days because there were
86 days. And the whole sea was full of this thing, oil, about 6.
Is it that the technology was not there to contain it earlier than that?
Yeah, there was a company called, I think it was Wild Well Control, who built their own capping stack. And they were, when it happened, like people were trying to come up with a way to cap it, like a prototype way. That's why nowadays, a lot of the developments is in the subsea capping stack technology.
Yeah.
We have good ones now, better ones. But, the last accident like that in the Gulf happened in 1979 in Bay of Campeche on the Mexico side of the Gulf. And, those accidents don't really happen very often, but every time you learn something and you progress, so the next time you won't be that unprepared. There was a lot of issues that happened, and the BP got a lot of heat. Of the way they were doing stuff. But the way the accident happens versus what you do after is completely different. It's a completely different question, right? For instance, what Hakim is doing for his PhD is for what happens after you get a blowout, right?
The post.
Yeah. You want to know before you get a blowout what to do after, right? You want to be prepared. Now, what you do not to get the blowout is things that you guys do on the simulator, right? You are trying not to get a blowout, right?
To prevent kick and all.
Yeah, or the good cement job, make sure that you test it properly. These are other stories. Like why they got a blowout is a different story, and blowouts happen pretty often. It's just especially onshore actually. With the old wells, old rigs, etc., etc. But most of them are like, tiny. This was a big one because, I mean, it sank the whole platform. Right? It became, caught fire, it lost the whole, it's very different kind of. It's a situation where something small became bigger, 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 a lot of mistakes all together, and then basically they, yeah. So it's a different sort of story. The Santa Barbara one was a very easy well. Like they have drilled a lot of wells. It was well number 21 from that platform. So they really knew how to drill wells in that area. But they were unlucky. It was a strike slip faulting region. And they had the waiver not to case the whole well. They only cased like a short section. So, okay, they got the blowout. When you go to shut in, regardless, you are going to get pressure build up, right? You are going to shut in a flowing well. The pressure will build up. Now, if you haven't had casing in the well at the time, it's really your fault because you cannot do anything now. I mean, you have to shut in the well. And the best option, which is not something anybody will take, and I don't think they should take, is like let the reservoir flow until it stops, right? Now, you try once, you get an underground blowout. Okay, you go again, you open, you go again, you go again, you go again. Eventually, you will get because the depletion of the reservoir will remove enough fluids so that you can shut it in safely. But you have caused a lot of disaster until then, right? You already caused a lot of damage. But yeah, and of course, because it was strike slip faulting, it was easier for the oil to make it up to the surface because of the faults. It could get between the faults and move up. In Gulf of Mexico, it was Gulf of America now. It's normal faulting. So it's more, it's harder to make it up, even if they have the underground blowout. It might stay, it might get arrested by, it might be contained easier because it's normal faulting. Yeah, in Santa Barbara, it was a little bit of it was a very shallow well, very, very easy well to drill those. It was very, very, and a very nice place to drill wells. And unfortunately, because of that, you guys cannot work there. It would have been a nice place to work. Okay, so this subsea capping stack is a main thing now. And this slide basically explains that story that I told you, what they said. If the pressure goes above 7,500, good. If it goes below, bad. We open. And it actually went in between, and they were monitoring. And how they came up with those values is with very simple calculations. Yeah. And actually, it's irrelevant, but the bubble point of that reservoir was around that. So if you want to model around that value, 6,500 psi. So if you really want to model reservoir-wise fluid flow in that reservoir, you started from almost 12,000 psi, and you drop to something like 94. You were well above the bubble point. So it was single phase flow in the reservoir. There was a little bit of water, but it was residual. So the modeling of that was very, very easy. Capping stack shut-in strategy and pressure buildup. This is, you can do it in two ways. You can do it in an abrupt manner where you shut in the well abruptly, okay, and the pressure shoots up. Or you can do it in steps, in what we call incremental multi-step shut-in, just like they did it here. Over 1 hour, they got 6 steps. So every 10 minutes, you drop the flow rate by 1/6. This is what they did in Macondo. But there was the number of steps and the time interval was arbitrarily selected. Now, it also depends on when you install the capping stack. It's a very, very complex situation where you basically have to use Bernoulli to align it on top of the plume and then get it installed. And once you install it, it's running. Not running, oil is flowing through it, okay? It's abrading it. It's abrading it. So, okay, if you are gonna use 6 steps over 1 hour, can your coupling stack take all this abrasion over 1 hour? It might not be the case. So this is where a lot of technology is being done. If you can implement a shut-in over 24 hours, let's say, instead of 1 hour, you make it less likely for you to get underground blow because you're gonna take it more slowly. It's gonna be a more gentle shut-in. But yeah, I mean, it's gonna be hard to make a capping stack that can take such abrasion levels. Now, my drilling professor was in that committee, was in the investigating the Macondo incident. It was in the government committee that was investigating it after. And he was saying, after they cut the well, they should have, his opinion was that they should have opened it again to see how much how big is the flow and get an actual reading of how big is the flow. But to know, to measure, because the meters of the blood preventers were broken after the accident. So they didn't know how much was the flow. They were trying to estimate it. And things like that are important because when BP went to the court, they had to pay a fine based on how much oil they left in the well. They left in the water, right?
Yeah, the discharge.
So there was a big, if you read the transcripts of the court, there was a big discussion on like rock compressibility. Like, did they use, the people from USGS used what they thought a very high rock compressibility. And basically made the estimation of the simulations very high of the, or very low for the oil coming out of the well. So there was a lot of discussion with witnesses talking about why did you use this compressibility, rock compressibility? Why didn't you use a higher value or a lower value, etc., etc. So if you read those transcripts Hakim did, you will understand a lot of what was going on because it's basically just like reservoir engineering or like.
So how much did the court find the BP pay to?
Around 20 million, I think, but with everything, with everything, I think they were estimating in total it was gonna cost BP something like 60 million, the whole everything altogether.
And the company didn't collapse.
Yeah, 20 million, I think was the fine, right?
President.
Yeah. Well, at that time, BP changed CEO to an American one.
Oh, okay.
It was Cayman, it became Bob Dudley at the time, something like that. Yeah. But all this happened back then. And also that was an area where they had a lot of kicks. And as you know now, the mud window was very narrow. Okay. So it was hard to deal with it. It's like the same project as you are doing in your, it was a very narrow mud window. You can get underground blood fairly easily or further kick. So yeah, this is how it shows the difference between the two shut-in strategies, abrupt and incremental. Some people call it hard shut-in and soft shut-in, but this is bad because in drilling, hard shut-in and soft shut-in has to do with the way you some valves in the BOP, how do you have them configured when you do the shut-in? So the HCR valve. So we try not to use that name. Yeah. And this is what actually I worked on a little bit during my PhD. A small part of my PhD was on critical discharge flow rates. So you come up with critical values that you can compare against the actual WCD values and figure out what shut-in to use. Shut-in schedule, sorry. Like number of steps and time. Now, other well-controlled topics that we would have liked to go over, but we don't have the time, is during the kick circulation, how do you do pressure losses optimization and hole cleaning? Oops, sorry. This is how those graphs would look like. Circulating pressure losses versus flow rate. And then basically hydraulic horsepower on the bead and the total horsepower, etc., etc. We went over those in Texas. I had like 2 elective classes, no, 3 elective classes. The one was advanced drilling and well completions. The other one was managed pressure drilling and well bore mechanics. And the other one was blowout prevention and control. So we had a lot more time to go over this stuff. This was a nightmare homework, how to do it. I was planning to give it here, but we don't have time. What else? Yep. Horsepower optimization at a given pump flow rate for a given liner size. There is a lot of stuff you can do here. Horsepower optimization at a given pump flow rate for a given liner size. This is things that you can also investigate if you have a project. Horsepower optimization at a given pump flow rate for a given liner size. And that was module 4. We learn what causes kicks, well control calculations, primary kick circulation methods. We really saw 3 main ones, or 2.5. Additional complications during gas kicks. Kill sheet examples. You need to know how to fill a kill sheet. And as you saw, it's not hard. The one that the pictures I showed you of the kill sheet. Like how to fill them. And underground blowouts, we talk about those. Now, oh, and post blowout well capping. Okay, we did talk about that. What I'm talking is about this stuff. You need to know how to fill those. It is not as intimidating as it looks because we went over it. And it actually says what you need, how do you calculate them, etc., etc. I mean, look, look at that. It even shows you plus, equal, times, whatever. So you need to be very comfortable in filling those because if you take a well-controlled certification class, this is what you are going to have to do. Now, since there won't be a review, I guess, ahead of the final, or there might be, I don't know, I will tell you, I gave you guys a hint. When did I give you a hint? When I said, I want you to know how you derive these equations from this, from Boyle's law, basically. I want you to be very comfortable because I don't have all the steps here. And I don't know a book where there are the steps. There must be a book somewhere. But, and I told you this number 4 is not the same as this number 4.
Okay.
So I want you to be very comfortable in evaluating, deriving that. Okay. Now, the last module we are gonna look at is gonna be module 5, which is gonna be a pretty short one. It's only 19 slides. And you don't really learn anything new in this module. You learn new stuff, but you don't learn a new concept. You already know how to do managed pressure drilling. You just don't know it yet. It's like applying what you already know in a different manner. Okay, and this is as cutting edge as we are gonna go through. Okay, these are stuff that people are doing these days, or especially back before the oil price dropped in 2014. Everybody was excited about managed pressure drilling. I remember when I was graduating, 2013, we had a student, you know, in the paper contest, an undergrad finished third that year. Undergrad in the bachelor's division, and the title of his presentation was managed pressure drilling. So, okay, classic objectives in drilling. You want to go deeper, cheaper, right? There is no doubt about that, right? Okay. And you also want wider windows, which you can appreciate now after your project. Like you want a wide window. Like if you wanted to cheat on your project, let's say, you could go where the gradient, the fracture gradient is, and you will make it like from 14.7 to like 20. And then you will never get underground blowout, have the pressure as high as you want, and then get the kick out, right?
Okay.
I mean, it would look wrong in the graphs.
Okay.
Yeah. But this is why you want wider windows, right? And there are areas like Macondo was a good example where the window is very small between pore pressure and fracture pressure. Like, what was it? 2 ppg, 2.5 ppg. It was very, very narrow. So if you get a kick at that point, you are going to have trouble. Now, we are using managed pressure drilling. It's a set of techniques we can use to control the risk and the cost of drilling wells that have narrow downhole pressure limits by actively managing the wellbore pressure profile. Basically, now every well, even the wells I was working at in East and West Texas, they were using some form of managed pressure drilling. It's a smart way. It's smart ways, and you will understand when I explain it. Okay. Here, what do we see is that okay, you have the two lines, the pore pressure, fracture pressure. Okay. Now it says wellbore stability pressure. That's basically where borehole starts collapsing, okay, which is behind the purple pore pressure. Now, when it comes to managed pressure drilling, it's the yellow line, okay, which is very narrow, right above the pore pressure, well below the fracture pressure, okay. No OBDs or overpressure, overbalanced drilling, okay, which is normal, what we have been doing so far. We are well above the pore pressure, well below the fracture pressure. Now, managed pressure drilling, we are staying very low, close to the pore pressure. What is the advantage of staying very low to pore pressure, having a very low mud weight? You don't have any lost circulations. That's an advantage, right?
Yeah.
Also, having to mix lighter mud is also an advantage. You use less barite, right? And things are easier to control. It's generally an easier operation if you can keep it here. But it's dangerous because you can get a kick. So how do you prevent getting a kick? How do you have low pressure but controlling the well? So advanced techniques used in modern day drilling, blah, blah, blah. You put a back pressure in the annulus side to make up for what your mat cannot press. So how is it? Just like we have a blowout and then we shut in the well and we have a pressure at the drill pipe side and the casing side. Imagine during the actual drilling of the well, the U-tube goes from a DPP value, drill pipe pressure on the standpipe, to 0 on the flow return line, right? Okay, now imagine if it doesn't go to 0, it goes to 100. What does that do? Anywhere in the U-tube model, you have to add 100, right?
To cater for that.
Okay, that means if my mat cannot provide me the pressure to hold the formation and I'm missing 100, that 100 can come from the surface, from the choke side, right? I just don't have the mat coming back out at atmospheric pressure. I have the mat coming back out at a certain value. Now, how we do that is a different story, but I cannot have it return at the normal flow return line. So, yeah, adjusting mat density and rheology, adjusting angular fluid level, controlling the circulating friction, incorporating hole geometry in well construction. These are all ways you can, different ways you can control the pressure. But the main one is the top bullet point, controlling back pressure in the annulus choke. Now, some other advantages that you can get from these kind of operations is that well control is easier. You get less non-productive time, improves drilling efficiency. You drill faster because your mat is lighter. Okay, you actually drill faster, I forgot about it. And higher efficiency, what is this mechanical specific energy? And of course, it's safe for the personnel and helps mitigating drilling related issues such as low circulation, wellbore instability, and less likely to get stuck pipe. So a lot of advantages right there, a lot of advantages. Now, there are 4 main variations of MPD. The first one is the most popular one. Well, when I say there is 4, there might be 7. You know, it's like some of them are under development, they are not used commercially yet, etc., etc. It's an area of active development. But a very common one is the constant bottom hole pressure, CBHP method. Okay, this is, think about the name. Constant bottom hole pressure is what I described earlier. You maintain a constant BHP by adjusting the flow rate of the drilling mat using a choke or combination of both. So instead of having the mat come out of the well at atmospheric pressure, have it somehow come out at 1,000 psi. Apply back pressure to it. So it comes at 1,000 psi. Then the whole U-tube model will add 1,000 psi everywhere, right? So I might be using a lighter mat, but I get what I'm missing, this 1,000 psi from the surface. Now, how am I gonna do it? I will use a special equipment of the surface called the rotating control device or the rotating control head, which is like an angular preventer, but it's placed on the choke side. And this is how you apply back pressure. But how it works, I don't really care. I just care about the principle. Because in several years, they might have different ways to apply this back pressure. But it's still the same concept, is the U-tube model with 1,000 psi added through it. Do you remember in homework 3, I think, there was a question that said, draw the hydraulic loop, but with 500 psi pressure in the annulus? And you saw that to do it right, you just shift the whole hydraulic loop to the right by, that's basically managed pressure, that's a managed pressure drilling problem. That's why I told you, you know what is managed pressure drilling, you just don't know it as a technology. It's the same thing, the same thing. What I'm saying is that it was something like this, and then it went like this, boom, 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 something like this to 0. And then it started at 500, so everything went down like this, like this, like this. Everything got shifted by 500 psi. That is because of managed pressure drilling. Same mud weight, different pressure. Yeah. Another method is the pressurized mud cap drilling. That is not used for the entire well. It's used for different small sections of the well. And that is basically pumping mud without any returns. So it's sacrificial mud. Everything you pump down, you are gonna lose it. They use that kind of drilling during when you are gonna drill through a cave, a cavern, something that you know you are gonna lose mud no matter what you do. So you pump. While you are drilling, you are pumping mud faster than what you are losing. So there is a continuous mud cap, pressurized mud cap. So it prevents you from getting a blowout, but you lose everything that you are pumping there. This method involves pumping drilling mud into the wellbore at a pressure greater than the formation pressure, creating a mud cap that prevents gas or oil from entering the wellbore. Sometimes a non-pressurized mud cap is used to prevent oil gas from entering the wellbore, but without maintaining a high pressure condition. So you also don't want to fracture at the same time. So whatever you pump is you're gonna lose. So,
but does it make economic sense?
No. Well, a lot of parts of drilling don't make economic sense, but it's for that section. How are you gonna go through that section? Once you run casing through that section and you are safe, you are good. You're gonna proceed. But I mean, you have to face that. I mean, carbonates, drilling in carbonates, sometimes you face those karsts. You know what is a karst? It's like something bigger than a normal pole, smaller than a cavern. Cavern is huge, like maybe this whole room of empty space. If you drill through that, you're going to lose a lot of mud. Karst is smaller than that, but still it can cause you problems. A lot of stories of mud circulation issues from the past, especially before, technology wasn't as advanced. You didn't know what you were encountering. Especially in wildcat wells, you don't really know what you are going to find because nobody else drilled there. Now, if you go to drill a development well, okay, you have seen the reports from other wells, okay, these people had no circulation at this depth. Now I am careful at that depth. I know I'm going to encounter the same formation, I mean, it could be, I know what I'm expecting to see. The third one is dual gradient drilling. And this is also a very interesting technique. It's used for offshore wells. And again, this, you know how to do it. This is when you have inside the marine riser mud that is the same depth, the same weight, sorry, as the seawater.
Yeah. Do something.
Huh?
Yeah.
Now, if you do have, in the project, you have to fill up the marine riser, and it took time, right?
Yeah.
And you're injecting at 100?
Yes, but it was not complicated like the other one where we're circulating the kick jetting.
Yeah, that was the worst, circulating the kick. Yeah, it was.
If you're not careful, small time you get it.
Yeah. Did you open above 40%? Okay. And the worst thing is when it comes up.
Yeah.
There was a student who started circulating, it was undergrad. They had to do it with the two circulation methods. They started circulating before the kick was out of the well. When the kick was in the yellow narrow section of the right, and they started the new mud then. So they were making it even worse because when the kick is in that yellow stripe on the right, that's the worst time. That's the highest SICP you are gonna get, right?
I think one occasion we got a blowout over there. So
over there?
Yeah.
That's the worst point.
Yeah.
That's the easiest place to get an underground blowout. But they started the second circulation early. So they added the heavier mud before the kick was out of the well. And that makes it worse. But this is not unlikely to happen in real life because in real life you don't know. You may have two kicks in the well. You may have a big one and a small one coming after. You may have three. You may have four. You don't really know. So when they do circulation, for you guys is one circulation or two, if you are using driller method. For the people on the field, it's like 10, 20 or something. They keep circulating for days to make sure everything goes out. Yeah. It's a well-controlled situation is a big problem. Anyway, dual gradient drilling, I have different mud inside my riser until the sea floor, and then a different mud weight underneath. What is the advantage of that is very important. The advantage of that is that it helps you with the casing design, okay? You are gonna need less casing strings if you do that method. Because if you put the weight of the seawater inside the marine riser, you are canceling out the seawater there. So it's as if you are drilling an onshore well. It cancels it out. So the casing design would be much easier in the sense of putting less strings inside the casing. And you understand the benefits of using less casing strings, clearly. Chevron has a boat, a ship, a drill ship, especially for dual gradient drilling. I forgot the name, but yeah. It's a complicated process, don't get me wrong, but dual gradient drilling is it makes things a lot better. There was a well in the Gulf called Blackbeard or something. It had 14 casing strings in it. 14, imagine. 1/4. So imagine how nice it is if we can go to less using that technique. So when we do that, and there are other techniques you can do to help your casing design, like pumping when running casing or having a back pressure, etc. But it's like it's much practical if you can use less. And the last one is under balance drilling. In this technique, the pressure in the wellbore is maintained lower than the formation pressure, which reduces the risk of formation damage and increases the rate of penetration, increases the ROP. But this one is like it's a little bit of an unofficial method because you need to figure out how to control the pressure at the bottom hole. And the best way to do that is with the first method, which is constant bottom hole pressure. So this is not really an official. It's not really an official MPD variation. It's not an independent. It needs to be coupled with something else. It won't be alone. Let's put it this way. Now let's see some images. Yeah, each method has its own benefits and drawbacks, and the choice of method depends on factors such as wellbore conditions, drilling objectives, and environmental considerations. Okay, I gave you here an article on managed pressure drilling that you may want to see from JPT. Oh, there you go. Managed pressure drilling. And there is a picture of Where is the RCD? They talk about RCD. I think there was no picture. Anyway. Okay. So slide 6. Okay, let's see the first one. Number 1, constant bottom hole pressure. You know most of the stuff about it. I remind you, homework 2, question 6 is what we discussed earlier. I was telling you, you guys already know how to do it. You have done it before. Now, when I was in a well in West Texas, on the reports, they used to say something like managed pressure drilling, 1.25 psi, ppg, sorry. You understand what that meant? 1.25 ppg of the equivalent mud weight or the ECD were coming from managed pressure drilling. Okay. Can you convert that to PSI at the bottom hole or anywhere? If you have the depth of the well?
Yeah.
You can, right?
Yeah.
0.052. Yeah. So you understand what that meant. Okay, this is the picture of the homework. And then we shifted everything to the right. From the solution key. This is from the solution key. So you see, I just added 500 on the surface and I was done. Now, how do I do it? It's a different story. Like, how do I do it operationally? But this is how it works. And I will use a rotating control device or a rotating control head, which is a key component. It is a mechanical device that is installed on top of the wellhead to provide a seal around the drill string while allowing it to rotate. It's like an angular preventer that is spinning. So it basically, it doesn't let the fluid come out of the well at 0 pressure. It comes out of the well at that pressure that you want it to come out. And then this way you control everything. The RCD is used in conjunction with a choke manifold to control the wellbore pressure during drilling operations. If you have $30 handy, and you don't know what to do with them, and I know I was a student too, I didn't have many dollars handy. I did, but I didn't. There is an online managed pressure drilling simulator from the same person who wrote your drilling simulator 3 that you can use on your phone, and it's basically doing that, exactly that thing. It shows you how you adjust the RCD to hold the back pressure, etc., etc. And it's not as it doesn't have as wide range as your drilling simulator 3, but the problem is that your drilling simulator 3 you always have 0 unless the well is closed. You cannot drill with the well shut in. Or maybe you can. I don't think you can. But yeah, it has this. This simulator is also a good teaching tool. If we had a class on managed pressure drilling, it would have been an elective class. I would have been using that simulator there for projects. But elective classes are nice because generally the exams are take home. There is projects in the class, and most people are already well experienced because they took the other classes. So, but anyway, we are lucky we have an advanced drilling class because in other places they only force them to take just one drilling class. Like Colorado School of Mines is just one drilling class.
Oh,
yeah, with completions at least. With a lab. Okay, so it's not, I think it's drilling only, but it's with a lab. So anyway, the RCD works by creating a seal around the drill string. Oh, we said that, sorry. Yeah, this is how it looks like. One of the key benefits of using an RCD in MPD operations is that it allows for continuous circulation of drilling fluids, even in high pressure wellbore conditions. This helps to prevent wellbore instability, low circulation, and other drilling related issues. RCDs are available in various sizes and designs to accommodate different wellbore sizes and drilling conditions. They are typically operated remotely using hydraulic or electric controls, which allows the operator to adjust the pressure and flow rate of drilling fluids in real time. So you may work in a company that creates RCDs, builds RCDs. So you make RCDs for different operations, right? Different conditions. We are not going to use the same one that you use onshore in West Texas in the Gulf, right? It's not. It doesn't make sense. You are dealing with different values, different pressures. Okay. Any question? The way it looks like, let me go back very quickly, since we have some time, to module 1, and I will show you how it looks like. Remember when we were talking about drilling with gas instead of mud? And we had this picture here. Okay. And we said there are some differences from normal drilling operations. And you have this thing here. This is a rotating head. It's very, very similar to what we use in managed pressure drilling. Very similar, not the same, but very similar. It prevents the gas, because you have gas flowing in and out of the well. Gas is always at pressure. You need to control that pressure. You can't let it outside. How are you going to control the pressure with a rotating head? So anyway, now, any questions on CBHP? Okay, let's move to the mudcap drilling. This technique, PMCD, is typically pressurized mudcap drilling, is typically used when drilling a well that has a high pressure formation or when drilling in areas of complex geology. A mudcap, which is designed to be heavier than the oil or gas that is being drilled, is pumped into the wellbore and forms a seal around the drill bit, preventing the oil and gas from flowing out of the wellbore uncontrollably. So the key word here that is not in the slide, but is dynamic. Okay, it's something that happens dynamically. You are pumping at a rate that allows the pressure at the bottom hole to be higher than the formation hole pressure, but you are also not pumping anything out. You're only pumping in. You have flow out, no flow in. Oh, sorry, you have flow in, no flow out, right? You're only pumping down. You are losing everything that you are pumping. The pressure of the mudcap helps to balance the pressure of the formation being drilled, which reduces the risk of a blowout or other well-controlled problems. So no mud returns, simple. It's a controlled low circulation situation, I guess. You understand what that means, right? Everything that I'm pumping, I'm losing. I'll lose everything that I'm pumping. Everything that I put down, I lose. but I do it at a controlled manner. The mud cap is maintained at a pressure that is slightly higher to the pressure of the formation drilled. This helps prevent any influx of formation fluids into the wellbore. You know what is the name of this influx of formation fluids into the wellbore? Exactly. Exactly. Very nice. The mud cap is also used to cool the drill bit and to remove the cuttings. Remove the cuttings means move them from out of the way, not bring them up to the surface. As, yeah, I mean, the way it's mentioned here is a little bit confusing. It is commonly used in offshore drilling operations and is considered to be a high-risk technique due to the potential for well control problems if not properly executed. So yeah, I mean, it's basically yeah, you're not gonna drill your whole well using PMCD. It's a section, only a section that you're gonna drill this way. Any questions on pressurized mud cap drilling or continuous mud cap drilling? Okay. You want to see about dual gradient drilling now, since we have time?
Yeah.
Yeah. So, dual gradient drilling is not onshore, it's only offshore. Okay, and it's what I mentioned before. You drill the well with two different grade mud densities. You have one mud density in the marine riser and a different mud density in the rest of the well. And now that you did project B, part B of the project, you guys are very well, you understand very well that you can have a different mud inside the marine riser. I don't think you can do that in the drilling simulator 3, but yeah, I mean it's possible. Usually, the mud density in the marine riser is set equal to that of the seawater, 0.465 for the Gulf. I need to change those slides. Cancels out the seawater column weight. So it's as if you are drilling onshore. Okay? It's as if we are at the bottom of the sea and we are drilling from there. And the design, the casing design is going to be from there. And it's going to lead to less casing strings needed, which is less money that you need to spend. So it's a nice fit. And this is how it looks like on a plot, I guess, or on paper. So one question that you guys should have when you hear me talking about dual gradient drilling is, okay, if I have a different mud inside the riser than the rest of the well, how am I going to be bringing cuttings to the surface for cleaning up and recycling the mud? And the answer is that this is going to be happening parasitically. Okay, you have a parasitic string that takes the returns to the rig, and then you clean it up, and then you bring it down to go here. So the mud here is different than the mud. The mud here is different than the mud here. Right?
Okay, yeah, because cut it down.
Yeah. Yeah. And I think I have a picture later on that is better. Oh, yeah. But if you see here, look at the difference in the design. Because now you know how to do casing design, right? Look, here I need 1, 2, 3, 4, 5, 6 casing strings. Here I can do it with 3. Yeah. Now this one, and you should be asking me, okay, why are the lines bent here?
Yeah.
And I will tell you, they use a different technique. that has a back pressure while you are running casing to be able to use even less casing strings. But even if, imagine if I was doing casing with the straight lines here, it would be the same thing. It would be not the same thing. It would still be less casing strings because look, let me use okay. Now I basically start from here, go like this, go like this, go like this, and then down. So I have 1, 2, 3, 4, and I have basically 2 less, even if I'm using a normal running of casing string. Let's see, instead of 3, I guess, I have 1 more, 1 extra, so not that much of you gain by having this canceling out of the seawater effect, seawater wave effect, by filling your marine riser with basically mud equal to the same weight as the seawater. Let me very quickly try to find a, oh, there you go. So yeah, this is how it looks like. Imagine a well with many, many casing strings and a well with less. Which one would you choose?
Yes.
The one on the right, right? Okay. Yeah, this is how it will look like. Before we leave, and we're gonna carry on next time, I want to see dual gradient drilling casing design. I want to show you something. I think the other class has an exam, that's why I don't want to keep them waiting too much. But look at this here. Oh, by INTC. Look at this plot here. If you start from, oh, it doesn't show it. Yep. If you start normal drilling and you have to fill the riser the same mud weight as you have in the rest of the well, you're gonna have 1, 2, 3, 4, 5. Otherwise, you only have 2. It's less casing strings. We're gonna see that in more detail next time. I just want to, I guess, because they have an exam. Let's finish. Have any questions? We're gonna finish that next time, the remainder 6 slides next time. But if you guys have any questions, let me know. Office hours today, 12 to 3 p.m. Make sure you attend. Make sure you attend
The mock.
the mock. Yeah. Oh, I'm getting a text from a UK phone number saying I need to pay my tolls. I don't know.
Need to pay what?
Tolls. You know, fraud. Like because 44 is the area code of England, right? Yeah. Well, why do I get that? I never drove in England. Anyway, thank you guys. I will see you on Thursday for our last class. Thank you, Donald. How was the project?
It was good.
Nice, nice. Stop recording.